Ashwani, please wait 1 minute. Okay. So, Ashwani, can you hear me properly?
Yes, I can hear you. Can you hear me?
Yeah. So, we have so many participants. That's why we are broadcasting through YouTube. Our session chair will collect the question from YouTube and they will convey to you after the completing of the session. Okay.
Okay. Yeah.
So during the talk, you will not interrupted by any question. After closing the talk, you will get the question from
You can actually interrupt during the talk also. It's totally all right.
No.
Yeah. It will be better if you
But we have more than 500 participants. That's why we are broadcasting through YouTube. That is not possible through Gmeet.
Right. Okay. Yeah. Okay.
Sajal sir, please inform me when we will be live. Okay, so let's start. Ashwani, may I share the YouTube link to you also? Okay. Okay, Puja, please continue.
Sure, sir. Good morning, everyone. Myself, Puja Chakraborty, Assistant Professor of CSE Department, BCET, and I will be hosting today's session. Today, we are on the third day and first session, and as a FDP host, I am going to start the session. For today's session, we are having Dr. Pramod Kumar Pal as a FDP chair. As the FDP host, it gives me a great pleasure to introduce a speaker whose academic journey beautifully bridges industry excellence and deep theoretical research. Mr. Ashwani Anand, a PhD scholar at Max Planck Institute for Software Systems, Germany, one of the world's leading research institutions in computer science. He has previously completed 2 prestigious internships at Amazon Web Services and has also been academically associated with Chennai Mathematical Institute. Mr. Anand's research interests lie in theoretical science with a strong emphasis on its deep connection with mathematics. With his solid academic foundation and extensive research experience, he brings valuable perspectives on cutting-edge development in computer science. We are truly honored to have him today with us, and we look forward to an insightful and enriching session. Please join me warmly welcoming Mr. Ashwani Anand. Sir, please.
Thank you so much for this kind introduction. I can just share the screen now, and we can start now. Can you see the screen?
Yes, completely visible.
Perfect. So you can see this now. Okay. Can I start now?
Sure, sir.
Okay. So, hi everyone. Thank you for joining today for this presentation. I'm Ashwani Anand, and I work in formal methods. I have a background in formal methods, and now we are trying to use this knowledge to make automated systems safer. So my talk today will be about how we can give formal guarantees on some reinforcement learning systems. So let's get started. So in today's talk, we'll see how from the left side, we go to the right side, where on the left, you see the rover is not able to land on the helipad, but on the right-hand side, you see that it always lands on the helipad. So this is what we'll see in the end. This is a small teaser for you. Okay, so let's get started on how we do this. So now we have AI systems everywhere. For example, on your television for motion smoothing, in your car, even in some space-related projects. And as the systems get more critical, testing becomes insufficient. So when you have less critical systems, you can test enough time the system, and you can say, okay, this works reasonably well, and this you can then deploy it. But when the systems become very critical, then you actually need to give formal guarantees where you have to say that you have to certify that nothing bad will happen ever, no matter how the environment is, no matter how the things change, nothing bad will happen. So these guarantees become really, really important, even from the business perspective. And if you are using it in some safety critical system, like in medicine, you have the lives are at risk, so these guarantees are needed. Let's look at a very simple scenario. This is not very critical, but we'll use this simple scenario for the talk to explain the topic. So here you see a warehouse where there is there are multiple rooms and there are paths between the rooms. So here on the left green side, we have a charging station for a robot. On the right hand side, there is a workstation for the robot, and there are in the middle multiple passages between the two rooms. So one has no obstruction, you can just easily go in and out from this passage. Then there is a passage where there is a slope. So since there is a slope, there is a chance that you might crash also if the speed is uncontrollable. In another passage, there are humans. So if you have to navigate through humans, it might take some energy or battery. Right? You will waste some energy going through a passage. If there is another room, another passage which has a lot of things, maybe like you can think it being used as a storage room or something. So to navigate, it drains even more battery. Okay. So there we have this robot which is trained to navigate this whole layout and to keep the battery charged. Okay. Now the question we want to ask is, can we really force the robot to also keep going to the workstation, right? So right now the robot is only concerned with navigating in this layout and then keeping the battery charged. But then the robot might just stay in this green room forever, right, to keep the battery charged. But we also want it to satisfy this constraint that it has to go to the workstation also once in a while to do its work, right? Then only it's useful. So we will answer this question, how we can do this. So to give answers, we turn to formal methods, right? Formal methods is a branch of computer science where we give guarantees, any kind of guarantees, right? So by guarantees, I mean, now we can certify that every execution satisfies a given property, right? So none of the executions ever will go to do something bad that we don't want, right? So we can give this certificate. On the other hand, testing would say many executions satisfy a property, but here we want every execution to satisfy the property. So we can, with the techniques we have, we can give these guarantees. So what kind of properties we are looking for? Maybe one is no bad state is reached, right? So you do not crash, you do not have a bug, so on. Another thing is liveness, right? So it says every request that you get should be served, for example, right? So your system has to keep making progress. It should not just sit idle or not do anything interesting, right? So this is called liveness, where we want every execution to progress. Formal methods has been used for all kinds of various guaranteeing in industry like AWS, NASA, Intel. All of these use our techniques to certify their products, to verify and to check whether there will be any issue after rollout. Okay, so today what we are going to do is we are going to see how we can enforce additional ongoing qualitative requirements at runtime on these trained systems. Right? Okay, so let's get started. So let's see some very brief formal definitions. I won't give like very formal definitions, so we'll work with this example. So here we have a Markov decision process. Basically, this is this graph-like thing where we have some states, then there are some actions. These actions like F, A, B, C, D, and E, which at a state you can take, right? So at a state, let's say at V1, you can take the action A, B, C, D, or E. At state V2, you can take the action F. At V5, you can take action G. Now, sometimes when you take an action, you don't know what exactly will happen. So there is a small chance if you take at V1 action C, there is a chance that you might actually go to V2 or V5, right? So so this is probabilistic, right? Sometimes you might go here, sometimes you might go here. Then on a transition, once you choose an action, then the stochasticity is resolved, you end up in another state, and this transition will give you a reward, right? So if you are at V2 and you take F, then you get reward 0. Okay, so what is a policy here now? A policy is basically a probability distribution over actions. So basically it says what is the probability of you, how would you choose an action at a particular vertex. So for example, let's say at vertex V1, state V1, you may assign probability 0.7 to action A. So then you will, when you will draw from this distribution, you will get an action and you will move with that. So here, the policy is basically just a distribution over actions at every state. And what is our goal here? Our goal here is to maximize average reward. So this is a bit different from standard RL system where you have discounted reward, but this is a more interesting case in today's talk for the reasons which will be clear later. So we want to maximize the average reward that we get when we keep moving in this Markov decision process. We also now want to ensure that basically we want to maximize reward while having this additional constraint of visiting V5 infinitely often. So this is the example that we saw earlier, right? The factory layout. Here V5 represents the workstation. So we want to see V5 again and again and again. Okay, so now the question would be, why not train the system with both the objectives? So one is optimize the reward, optimize for maximum average reward, and it should satisfy the specification that you see the workstation infinitely often. Now the problem is for these kind of qualitative rewards like visiting a state infinitely often and so on, the additional constraint we added, they provide sparse reward, which means like you will get reward not every time, but after a long run, and then you won't be able to know what actions you took which led to this reward, and then you cannot really learn what actions were you should take in order to gain reward. Another issue is that, again, if you train, let's say somehow you deal with sparsity of the reward. When you train, you cannot really, it's most of the time very difficult to give guarantees like, yeah, surely this specification will be satisfied, or almost surely even. Now, even if you, let's say, give guarantees, one more issue is that if now I change the specification, instead of saying infinitely often visit V5 is, I remove that, maybe we say visit some other state infinitely often, right? So then you will have to retrain with this new objective. Now, training is expensive, so we do not prefer that. Okay, so today what we'll see now is something called a shield, and we'll see how this can be used to actually solve our problem today. Then we'll see how to construct that shield, and then finally how we use that shield. Okay, so remember we have a problem where we want to optimize for maximal reward while satisfying some other constraints, right? So for this, we build something called a shield. Okay, so now what is a shield? Shield is basically an additional layer between your controller or your decision making system and the MDP, right? So the decision making system is going to choose what action to take, and then MDP, the action is taken on the MDP, and you get reward and so on. But we put a shield in the middle, which basically means that the shield will take the action from the decision maker. Then it will check for compliance for some specification, and if the action meets the specification requirements, then the action is sent to the MDP. Otherwise, we may change the specification as well. We may change the action as well. Now, what is nice about the shield is that you can just use another shield for another specification later. You don't have to touch the training part of your decision-making part of this whole system, right? And basically, this allows us to decouple the two objectives, right? One objective was optimizing for maximal reward. Another was the qualitative objective. Now we can decouple. Now what we can do is we can just train for this quantitative reward, the reward maximization thing, and we can build a shield for the qualitative property that we want to satisfy. And when we plug both of these together, we get a policy in the end that satisfies the specification and also tries to optimize for the maximal average reward. Okay, so well, the problem is shielding is also difficult. It's not that easy. So if you have to shield for some safety requirement that something bad does not happen, that's easy, and it has already been done for these automated systems. So here the thing is that when something bad is happening, you know that something bad will happen. There is a chance that you will go to a bad state. So you just stop that action and take some other action. So when this is happening, you can see that, monitor that, and then change your plan. But liveness, for example, visiting V5 infinitely often, that is a liveness property that is difficult to shield for, because you will never know if you are actually going towards this or not later. So for example, at V1, I can keep taking this action A and stay here. There is no way for you to tell me that I'm not trying to go towards the goal, because I might just say that, okay, next time I will go, next time I will go, next time I will go, and so on. right? And in even bigger graphs, it will be difficult to know if you are actually going towards the goal or not. And with finite prefix of the execution, you cannot tell me whether you are actually satisfying liveness or not. Even if you satisfy 10 times, even if you go to this state 10 times, I have no reason to believe that you will infinitely often go here. Another thing is that the shield should not interfere too much, right? So if I just put a shield and then basically the shield does whatever it wants, then that won't be nice. We have to consider the training part of the system as well, so that we shield only when we really need, right? So we do not just modify everything that was learned. Okay, so now that you know what shield is, let's see how we can construct a shield. Okay, so for this we play some games on graphs. Okay, so we will take this MDP and then we treat it as a game on a graph with two players. Right, one player is the circle player, which chooses the action, and the other player is the stochastic player, which resolves stochasticity. Basically, says where this which state will you go to, right? And the circle player wins if the specification is satisfied, right? That you visit V5 infinitely often. On the other hand, the goal of the triangle player is to not let the circle player satisfy the specification, right? So this becomes a game. Now, what we want to do here is to find a strategy to visit V5 infinitely often. What that means is a strategy basically means that no matter what the triangle player does, you will always be able to see V5 infinitely often. Right? So that is a winning strategy, and that's the strategy we want to find. Now, here, see that there are actually many strategies, right? So from V1, you can maybe take B or E, and you are guaranteed to reach V5, right? Also, I forgot to mention earlier, these gray line denote that from V5, there are same actions B, C, D, and E going towards V1. So notice that if I take, if my winning strategy is just go to E, take E and go to V5, then this is not nice for the training, because we saw that this would have cost us a lot of reward, right? So this is a bad move, and if you keep taking this is bad for our reward part. So if you just pick one particular strategy, that might not be compatible with the reward structure of the problem. Another issue is that, okay, now there might be infinitely many winning strategies. Now, if you have infinitely many winning strategies, which strategy to pick? How do we decide what action to take now? Should we take B? Should we take D? Should we take E? So now, since there can be infinitely many strategies, we also need to actually be able to find them so that we can choose one of them as and when needed. So instead of giving one strategy, what we give is something called a strategy template. Right? So strategy template is basically a guideline, if you will, that helps you choose your next action. So basically, it looks something like this. So here at V1, observe that if you go to C, if you take C, then the non-deterministic player, the stochastic player since its goal is to force you to lose, the stochastic player will send you to V2, and then you will lose. Right? So this is an action you should never take, because if you take this action, stochasticity might force you to go to V2 and you will never be able to satisfy your specification of going to V5 infinitely often. Okay, so this is, so when we are choosing an action at V1, we should for sure ensure that we never choose action C. Right, so this becomes our first guideline. Okay, the guideline is do not take action C at V1. Then another thing here is that we have already seen there are different paths to go to V5. One is B, one is E, one is D as well, because after taking D, the stochastic player cannot do much. It can either go to V3 or V4, from where you are guaranteed to go to V5. So B, D, or E, any of these paths are good for you at V1 to go to V5, so you can satisfy this specification. So what we say is, okay, infinitely often take one of these edges. So one of these actions, B, T, or E, right? So this becomes another guideline. So if you are at V1, if you don't want to take B, D, or E, you can take A for some time. I'm not saying anything about that. So take A 10 times, 1,000 times, 500 times. I don't care. But keep taking at least one of these edges again and again and again. You choose whatever you like. So now, instead of fixing one particular strategy, we have given some guidelines which can help you choose a particular strategy during runtime. Okay, so now these kind of guidelines that where we just disable some actions, we call them safety templates. And when we say take one of these edges, one of these actions infinitely often, that is live group template. Okay, I won't show in detail how we compute this, because that will be too much for this presentation. But basically, we can compute this for a huge class of qualitative properties. And in our work, we show that if you can satisfy these templates, you win the game that we wanted to play. And these templates can be computed fairly efficiently in practice for omega regular specification. So if you don't know what omega regular specification is, basically it is a temporal specification where you can say something should happen always, or something should happen eventually in future. You can say something should happen before something else. Something should happen 5 times, 100 times. These kind of things you can say, and then you can nest things. You can say, okay, something should not happen, but if it happens, something else good should happen, and so on. So this is a very big class of specifications, and it's very difficult to explain all of this today. But you have to believe me that we can compute them in practice very efficiently for the objective, the infinitely often V5 kind of objective, which we call Buki objectives. For those, we can compute the templates in big O of n cube time. So that's the best you can do. You cannot do better than this, but this is really good. In practice, it terminates very fast also. Okay, so for a huge class of objectives, we can compute these templates very efficiently. And now you see that instead of saying visit V5 infinitely often, which is a global property, I don't know how to reach V5. What we have done is we have broken down this specification into local specification, which says at this node you have to do certain things. Right? At this state you do certain things, and you will be eventually be able to satisfy your specification. Right. So basically, what the templates allow us to do is to take a global property and then decompose it into local properties that you can satisfy during runtime or whenever you are choosing your strategy. Okay, so we have seen we saw how to compute this and these strategy templates. Now we will be using these templates to shield our policy, the learned policy. So how do we actually use the templates and in the shield, and how do we use the shield in the application? So we have our MDP. Let's say we have trained a system that tries to maximize the average reward, and now we want to construct build a shield. What it basically does is it first asks you to pick a small alpha. What is alpha? Alpha is the enforcement parameter. This is a value with which we will perturb or change or modify our policy when needed. Okay, so let's say your policy says that at V1, sample A with 0.7 probability, B with 0.1 probability, C with 0.1, D with 0.1, and do not sample E at all. Right. So let's say this is what your after training your system learned. Okay. So now what the shield does is, I should say, let's just take for this example alpha to be 0.05. Okay. So what the shield does is the following. It takes the policy from the decision maker. Now it checks the policy against this the template that we just computed, and we see that since C was there is some typo. C should be 0. So in the rest of the talk, swap the values of B with C. Right. So sorry. So since C is not allowed to be taken here by the template, if you take C, you might just not be able to satisfy the specification. What we do is we make the probability of that being happening 0 in our policy. So again, sorry for this confusion. Swap the values of B with C. So C will be, or for now, let me rename these actions B and C. Okay, so B becomes 0 because we are not allowed to take those that action. Now the shield normalizes this distribution because currently it is not adding up to 1. We normalize it and we get some other distribution at V1, and now we will sample from this distribution. So this will ensure, notice that this will ensure that we never take an unsafe action, unsafe for the we never take unsafe action which is unsafe for the qualitative property, right? So this will never happen. Okay, then we sample from this normalized policy. Let's say this time we sample A. Okay, then what happens now is that every time we do not take the live actions B, D, or E, or now in this part, in this policy, it's B, C. So now every time we don't take these green edges, we increase their probability by alpha. So basically, what this means is that we are forcing the policy to tend to pick one of these green edges. So for example, here, since we did not take one of these green edges, we'll slightly change the policy in their favor. Okay, so then we will have something like this. We normalize this, and now you notice that the probability of A happening has reduced a bit. Probability of C, D, and E has increased. If we keep doing this, if we keep now sampling A, the probabilities will keep increasing. At some point, probabilities of the green edges being taken will increase. So for example, here it has increased again. It will keep increasing until we arrive at a point where the probability will just be too high here of these edges, and after normalizing, you will get higher probability on these green edges, and then it is more likely that you will sample from these green edges. Right. So basically, what is happening here again is that we are first ensuring that we never take an unsafe edge. Then we ensure that if we are not this one of these live edges is sampled, we revert back to the original policy. Basically, what that means is that we bring back the policy that the controller is suggesting, and just reset the values for these actions which are not unsafe. Right? So now that you have taken this action once, you know that you have made progress for sure, and then you do not need to really force your shield again to take the action. So you can wait a bit more now. Right? So we will continue doing this. If you are not taking live edges, we will the shield will nudge you to take the live edges. Eventually, the probabilities will be in favor of the live edges, and the live edges will be taken. And then you can stop nudging, then you can nudge again, and so on. So this is what we will continue doing. With the shield, we show that if you shield your policy like this, we will surely or almost surely, depending on what you need, we can do both. Surely or almost surely satisfy the specification that we have. Like visiting V5 infinitely often, we can do here, or other omega regular properties. You can do like this whole class of properties, right? But you might wonder, right? Like maybe we nudging the probability makes the reward bad, right? We also show that we actually interfere minimally. So basically, if you get a execution without without the shield, and compare it with the execution with the shield, you will not be able to distinguish much. Basically, the probabilities of both strings appearing from unshielded policy is very close, right? So basically, you cannot. Basically, we do not change too much. And then we also show that we are epsilon close to original policy's expected reward. What this means is that you give me any epsilon, like you want, so your policy gives you some expected optimal reward, right? You give me any epsilon, I can keep the alpha in a way that you will, while satisfying the specification, you will get the policy's expected reward plus minus epsilon, right? So you will be really close to the reward that you would have already gotten. So the shielding does not make your policy worse. It just adds another ability of satisfying a specification. So this is very important, right? Okay, and I didn't discuss this much, but the benefit of this shielding is that it is compositional. So what that means is if you have a specification, you can shield for it. Now later, let's say during runtime, another specification comes. Maybe let's say another workstation is built, and then you have to go there as well, right? So you can compose the shields the via strategy template. So you will compute shield for the other new specification. We will merge both of them, basically check for compliance against both the templates, and then we will have a shield that will shield for both objectives. So you can keep adding as many new objectives as you want online, right? So whenever you want, you can add. And again, we will not make your policy worse. It will just help you satisfy additional specifications. Okay, so basically, we took all of this and tested on, like we implemented factory layout benchmark, and then we tested our shield on this benchmark. So here is the UI where we basically we can play with the shield. So here basically what we do is we generate a grid layout. Here you see there are ones. One means that here you will get reward 1 if you come here, and 0 is which means if you come to this state you will not get any reward. Here is our robot, right? And then we first train to go to maximize our reward. So you will see that here without shield, here notice that without shield the robot is just staying in this one region, right? It does not want to do anything else because that is going to give it the most reward. But now if we want to actually go to the green region here, that's an additional specification on top of maximizing the reward, right? So if we want to go here, we can then activate the shield. Let me move it a bit, right? So now the shield is activated with an enforcement parameter very low. So now with very low, it stays in this one region, but once in a while goes to the green one. And if we increase it too much, then you will see that it goes more towards the green region than the optimal reward region, right? So with this enforcement parameter alpha, what we can do is we can tune how fast we want to satisfy our specification, and basically this gives the engineers or whoever is implementing the system to choose based on their requirements the how one second, let me pause this, how fast they want to satisfy the specification and how much they want to be close to the optimal reward. Here you see that we also added this green cell here, which is additional objective. This is compositionality that I was talking about. So now the specification is satisfy, like go to this green region infinitely often, and also this green region infinitely often. And we can online now modify the shield without stopping the system even. We can modify this in a way that it will now go to both the regions like right now, while also maintaining the reward. Now keep in mind that the reward you will get will change based on the enforcement parameter. Since the enforcement parameter is too high right now, it is only visiting these regions, but once in a while it will go and collect some reward in the one region that it's going there, right, to collect the reward and so on. Okay, so we saw that if we increase the enforcement parameter, we satisfy the qualitative property more, but we give up some reward. And if the enforcement parameter is low, we get more reward, and we visit the goal region less frequently. But for sure, we will visit the goal region infinitely often. It will be very slow, but we will still do it. Okay, so okay, here is the heat map of what was happening. So right now, the shield was turned off. So you see the heat map shows that the robot was basically staying in this optimal reward region. Then with low enforcement parameter, it is still staying more in the one region and once in a while going to the green one. But if you increase the enforcement parameter too much, then it will just move to satisfying the specification at the cost of reward. Okay. We ran experiments on bunch of different grids, and we get this observation that if you increase the enforcement parameter, frequency of visiting the goal state increases, but the distance from the optimal reward also increases. Like, you will not get the optimal reward. You will not get close to the optimal reward. Okay. Now, so far so good. But usually when we use reinforcement learning, we use them for unknown MDP problems, right? So usually you do not know the MDP. The system is just so complex that you do not know. So here we have this lunar lander benchmark, which is also a very well-known benchmark. It has 8-dimensional continuous space, and the underlying MDP is just almost impossible to know. Okay, so here what we want to do is to train the lander to land on this moon surface safely, and also land on the helipad. Right, so helipad you see here is this region, and you want to land in the helipad, not anywhere else. Okay, so for these, what do? We don't have the MDP. We cannot just solve the game and then force the nudge the policy to take certain actions and so on. Right. So then, what we do is the following: we take our scenario, we discretize it. Basically, we make a grid on this world, and you see there are no cells here. And then this gives us a game graph where the edges are just by the next cell relation, right? So if you fire the left engine, you will go to the right cell. If you fire the left engine, you will go to the right edge. Yeah, and so on. So basically this. And then we solve the game on this graph here. The specification we wanted, the objective we solved for was the following: infinitely often visit the blue region, right? And in the orange one, do not go to the orange region. Right? This was just done because our discretization is extremely coarse. There are 8 dimensions. We only use 2 dimensions, the XY coordinate. We did not consider the speed. We did not consider the angular velocity and so on. The discretization was extremely coarse. So we added a bit of safety net so you don't land here. Okay. And okay, this is not playing, I think. Okay, let me show it here. Right. So basically, after solving the game, we now use this abstraction to choose our actions in the original world. Where is it? I'm sorry, I'm having some technical difficulty. Okay, yeah. So you see now that the lander is kind of trying to go stay towards the blue region, right? So yeah, it does not deviate too much. And here we have kept the enforcement parameter low, so it just slightly nudges towards the blue region, and that is enough. And you will see that it will now land on the helipad. Okay. Yeah, almost there, right? So you should observe that it stays very close to the blue region. That is because of our nudging towards this, and it has safely landed. Okay, so this is how we deal with this. So we take this scenario, we discretize it, we form a game graph with this discretization, and then use that to shield the action. So if I'm in this particular cell, if my template says go right, then I will ask my policy to fire the left engine and so on. Okay, yeah. So here you see what happens when we have no shield, right? So the lander tries to land, and it will deviate at some point here, right? So it deviates and goes away from the helipad, and it does not land, right? So it will just stay hover there, and the episode kind of ended, and the whole clip is not there. But the point is that it went very far away from the helipad where it was supposed to land, and then it didn't land there. You have already seen what happens when we keep the enforcement parameter low, which means like we are saying, okay, the blue region, you go towards that slowly. Okay, now let me show you this one. When what happens when yeah. So when the enforcement parameter is high, we are basically forcing it to satisfy the specification more aggressively. So you will see that here it's more aggressive, right? Like now it forces too much towards the blue region, so it is a bit unstable. But then the training is good, so it recovers, and then finally it lands. So you see that this is a bit more aggressive and a bit unstable. So if you keep the enforcement parameter very low, then you will land more smoothly, right? And yeah, so we yeah. So basically, one more thing is you can keep the enforcement parameter very low, and as long as it is greater than 0, we can show that you satisfy the specification, right? Just choose very low alpha, and then you will be good. But if you somehow for some reason need to satisfy your specification faster, then increase the alpha, but then you will start losing reward. It's a trade-off, right? Okay, so in the lunar lander example, we took our shield, compared it with a safety shield and no shield. So liveness shield was, we say that go towards the blue region. Safety shield says that do not land. The safety shield, this is previous work by other people, it says do not land outside the helipad. These are two different things, right? So we say go towards the helipad. Safety says do not land outside. Now, what this means is that the safety shield can only ensure that it does not land outside, but it does not say how to go towards the helipad. So the lander basically just hovers in the air. It does not know where to go, right? But with liveness, we target it towards the we are able to target it towards the helipad. And when there is no shield, you see that in around 10% times, even without shield, it lands because it's just lucky. With safety, with just safety seal which says do not land outside, around 33% times it lands on the helipad. But with around 89% success rate, it lands on helipad if we use our liveness shield. Okay, so it's pretty good. Like also the episode length was around 10,000 time steps. So if you let it run longer, like so basically the after the cut of 10,000 steps cut off, we do not know what happened. So if you let it run longer, liveness shield will the chance of the lander to land on with this liveness shield will increase, right? So eventually it will for sure land. Now one more thing we noticed is the following. So this is the average step count for landing, right? So we we count how many steps it took for the lander to land on the helipad. Now you see that when we use our liveness shield, we take less time to land, right? Around 4,700 on 4,700 average steps compared to safety shield where it took more time. The reason was that it just hovered over the land. It didn't know where to go. Luckily, if at some point it came just above the helipad, it would land then, right? So it took too long. With yeah. So basically, what we do is with this targeted nudging, we are able to first land more often in this limited time frame, and we are able to land faster than the safety shield. We do not have comparison with any other liveness shield or any other way of liveness shielding because there is no other there has been no prior work of shielding for liveness properties. So we are the first to do this, right? So yeah, with this I would like to end the talk, and I will be happy to answer questions. And also please feel free to contact me if you are interested in doing this kind of work with like on safety and certification of AI systems. So we are always looking for this kind of work, and we are currently doing a lot more in this field. So if you're interested, please feel free to contact me. And now I can answer questions if you have.
Pal sir, please proceed.
Hello.
Pal sir, can you hear? Pal sir. Pal sir, can you hear me? Puja, please.
Yes, I can hear you, sir.
Yes.
Sir, yeah.
Okay, sir.
Sir, please conclude, Pal sir.
Good morning, all of you once again. So this is a very nice presentation for formal method for guarantee on reinforcement learning systems. So first we introduced to Mr. Ashwani Anand. It's my pleasure to this FDP as a chair to introduce Mr. Ashwani Anand, a PhD student in Max Planck Institute for Software System in Germany, a leading global research institution in computer science. He has previously completed two internship at Amazon Web Services and has also been associated with the Chennai Mathematical Institute. His research focus on theoretical computer science, especially its close connection with mathematics. With his strong academic and research background, he brings valuable insight into cutting.
Pal sir,
Uh-huh.
please give the question to him first.
Okay. So, Mr. Anand, one thing is that what is purpose of formal method in software development, sir?
So basically, the purpose is that you want to guarantee the specification no matter what, right? So for example, if you have a software which is, let's say for a coffee machine, you don't need to do much. You can test it 10 times, 100 times and so on. And then you can say, oh, most of the time it makes coffee. But if you're using your software for medicine purpose, like for a medical device where life is at risk, or you are sending a rover to Mars where the repair is costly, then testing won't be enough, because okay, you can test 1 billion times, but maybe there is a issue in some execution which you didn't see. So the idea of formal methods is that we guarantee or certify that no matter what happens, every execution satisfies some properties. For example, that nothing bad will happen, or the system will actually perform its task, what it is designed to do. So the purpose of formal methods is just to guarantee that no matter what happens, your system is safe and it does what it is designed to do.
Okay.
Which is costly, but it is necessary when you have a safety critical system.
Okay. So very nice answer. One is also question is that which solution are part of the reinforcement learning from human feedback design?
So right now we are there are now some work in our group on human feedback based reinforcement learning, and then how we can use shielding or our formal methods techniques to guarantee certain things there. But so far there has not been too much work in certifying those systems. But it is a future direction that we are looking at.
Just like SMT method, something is that.
Yeah. So it is real. So SMT kind of things. So AWS uses a lot of SMT formulation and validation for their systems. But for automated systems, these trained AI systems, this is still very limited, right? But it is a work in progress. I worked with AWS on something similar. So we used SMT solvers to guarantee something on chatbots, their chatbots, LLM chatbots. Okay. So we can give guarantees that it will be grounded in the document that it reads and so on. So these kind of guarantees we are now able to give, but it is a work in progress.
Okay. So,
Pal sir,
yes.
please 1 minute. I think Puja madam also collected some questions from participant. Puja madam, please proceed.
Okay. I oblige.
Thank you so much for the wonderful and nice session, sir. Thank you so much. So from the YouTube chat box, here I can see a few questions and would like to highlight those questions. One of the question is that in one slide you have mentioned strategy templates. So on that particular slide, you have mentioned that templates can be computed efficiently. So can you please once again repeat how we can compute those templates?
Okay, so how to compute, I can briefly say. So we deal with this omega regular specification. It's huge. I won't basically talk about that right now, but for this objective, which we said was visit a node infinitely often. So these are Buki properties. For this, what we do is we basically take the goal set and see from where we can reach in one step, and then in 2 steps, and then in 3 steps. And this will give us all the states from which we can reach there once. Then we find out from where we reach once more, like 2 times, from where we reach 3 times, and so on. So we continue doing this process until we cannot grow the region anymore. And then we have a set from which we know that we can reach the goal set infinitely often. So this is a fixed point algorithm. Basically, you start from a small set and you try to grow it. And basically, this is what we do. It in the worst case takes O of n cube time, right? But in practice, when we ran experiments, it was extremely fast. Even for millions of states, it ends in 20-30 seconds. So the worst case for omega regular is quasi polynomial. I mean, you don't have to go into that, but it is not polynomial. It is difficult in worst case, but in practice, it runs extremely fast, and we can find these templates very fast. So I just gave you kind of a vague intuition of how we compute for Buki, but for omega regular, it's much more complex. So yeah, but there are ways of doing this, and we have mentioned all of these in our paper. So yeah, if you go through the paper, you will find them. If you have any issues, contact me. Yeah.
Okay, that's all for the session. Thank you so much.
Thank you.
Pal sir, now please formally conclude the session.
Okay. So finally, very nice this session regarding to Mr. Ashwani Anand. So actually, this is based on the theoretical. Okay. So this is based on the formally theoretical computer science, especially formal method of guarantee on the reinforcement learning. So
I think there is a technical glitch from the PAL sir's window. So on behalf of PAL sir, I would like to conclude the session. Thank you, sir. Thank you once again for delivering such an insightful and engaging FDP session. Your expertise and clean articulations truly enriched our understanding and made the session highly impactful. And moreover, the active participation made a meaningful learning experience. Thank you so much, sir.
So
thank you so much for inviting.
Thank you all of concerning is that for entire concerning teams and for this nice session. So very nice, Mr. Anand. We call you again for other my programs. So especially, so thank you very much once again.
Thank you so much for inviting.
Okay.
Thank you so much.
Thank you so much for your time, sir. Have a great day.
You too. Bye. Thank you.